Hello and welcome to the Unit 6 podcast on section 14.3. Today we're going to be talking about the ideal gas law, and I'm Mr. Sakuchi.
I'm Mr. Lin.
So let's begin. The ideal gas law basically takes into account the amount of gas that is present.
So previously, when we're manipulating pressure, volume, and temperature, that was all assuming a certain, exactly 1 mole of gas.
Well, no, it was a constant
Or
amount
a
of gas.
constant amount of gas, my mistake. Well, that can be changed, and if that occurs, we have to be able to calculate for that.
So if you compare this to our combined gas law, we've added this component N, and N refers to moles of gas. Now, in an ideal gas law, well, previous up to this point, we've always had two sets of conditions to compare, right? In the ideal gas law, what we do is we set one side equal to ideal conditions. So remember, ideal conditions for gases is going to be under STP conditions. So that's 0 degrees Celsius, which is 273 K, 1 atmosphere. Now we know under these STP conditions, the amount of moles of gas present will be 1 mole. And then we know that based on Avogadro's principle, that 1 mole of gas will have a volume of 22.4 liters. You plug these numbers into here, and that's where our constant R comes from. What you'll find is that R will vary depending upon what units of pressure we're actually working with. You can see here on the right that R can vary depending on whether we're working with pascals, torrs, or other types of units as well.
So the different types of R's they all apply to the same amount of gas, but the thing is that they're just different units of measurement. Just like for measuring length, you can use inches or centimeters. It's for the same amount of substance. It's the same substance. It's just different unit for measurement.
For us, it'll be what varies will be what units of pressure we're using in terms of either atmospheres, torrs, kilopascals, or millimeters of mercury. We talked about how the kinetic molecular theory doesn't necessarily apply to gases under all conditions. Non-ideal conditions are basically when we have gases at high pressures and low temperatures. And the idea here is that under these conditions, some of the assumptions we make no longer apply. Things like attractions. We don't take into account the ability of gases to actually change state of matters as well. So this is where we have limitations of our gas laws.
So our ideal gas usually has low pressure and high temperature, and what that sets up a situation for is that the gas particles run by and hit each other so fast and so often that none of these other interactions really take apart. But when you start having high pressure and low temperature, they slow down to the point that these other interactions can occur, where they can attract each other or even react with one another.
If we're going to work with real gases, they would require correction factors to the gas laws that we've been using, but that goes beyond the scope of this course. So just be aware that these limitations exist. You won't have to calculate anything involving them, though. How do we use the ideal gas law besides just using the ideal equation? We can actually manipulate it and solve for densities of gases as well as molar masses of unknown gases by doing the following. So for instance, if we take and we change N to grams over the molar mass, which would give you moles, you can derive these. I'm not going to bore you with them. The take-home message is that we can use these two equations here to calculate molar masses of gases, and then we can use this equation here for calculating density.
So if we handed you a balloon of gas, of one type of gas, and wanted to find out what it was, you could just pretty much take measurements of it and find out what the exact compound is. And that's what it's for.
Mm-hmm.